everybody. My name is Julie, and my dad is going to teach you guys earth science.
Okay,
Bye-bye.
Thanks, Julie. Bye. Just a heads up, we got Radioactive Decay today. This is something new. It can be a little bit confusing, so make sure that you stick with me and pause if you need to. I would like it if you filled out your note sheet today, obviously, and get through questions 1 through 7 on the worksheet that goes with it. You got Castle Learning and the Sequence of Events Lab that will be due on Saturday and graded on Saturday. So please make sure that you get them done. Also, little heads up, on Monday I'm going to be posting a quiz. Please make sure that you get that done as well. That will be graded, but that's for next week. So today we're going to be starting to talk about absolute age, where that is different from what we spoke about last week, which is relative age, all right, which we'll get into in a second. As far as our do now questions based on fossil evidence, most scientists infer that, all right, so which one of these statements would be true? Go through one by one. A lot of these are going to be referencing your pages 8 and 9. So choice A, life has not changed significantly. I don't think that's true. Many organisms that lived on Earth have become extinct. That holds some merit. C, mammals developed early in the Precambrian. If you look here, mammals really didn't come about until right around here in the Triassic. So that's not true. And then D, life has evolved from complex to simple. That's not true. We actually go the opposite way, simple to complex. So your answer is going to be B. And if you look, most of our organisms that were on the planet did go extinct. A lot of those bars that you see here ended. Okay? So a lot of organisms have gone extinct. All right, number 2, scientists believe that a large asteroid struck Earth approximately 65 million years ago. It is often theorized that this event contributed to, all right, let's go to our page. 65 million years ago, right around here, it says it right there for you. Mass extinction of dinosaurs, ammonoids, and many land plants. So, bada bing, there's your answer. Number 3, which 2 landscape regions in New York State have the oldest surface bedrock? Oldest bedrock. So if you look here, oldest is furthest to the bottom. Okay, so you're going to be looking for Cambrian, or you're going to be looking at anything over here that says Precambrian or Proterozoic. So in order to answer this question, you're going to want to go to these pages saying which landscape regions are made of the oldest bedrock. Well, here's our bedrock page. And the oldest bedrock is this stuff. All right, Cambrian, Proterozoic. And if you look, that's over here. And that's over here. All right, so if you go back to our page here, look at where we land. All right, we land in the Adirondack Mountains, and we land in the Hudson Highlands. So your answer should be Adirondack Mountains and Hudson Highlands. All right, so new stuff. Here we go. All right, this is all review. We got this. Okay, so difference between relative dating and absolute dating. And if you remember correctly, relative dating was when we were saying that this rock is older or this rock is younger, right? And that's based on all our laws of superposition. We had our cross-cutting law. We also had our original horizontality law, right? We all understand and should remember that stuff. If not, you should be going back and making sure that you understand it. But either way, when we talk about relative dating, we use words like older and younger. No numbers. Now that is going to be different than absolute dating. Absolute dating, we will be using numbers. We will be discussing the actual age of stuff. So if you remember our first day, we were saying that I, Mr. Mitch K, am younger than Mr. Stagnita. That's relative dating. Absolute dating would be I, Mr. Mitch K, am 34 years old, and Mr. Stagnita is 4,000 years old. Okay, that is absolute dating. Okay, moving on. All right, so how do we find out actual ages? We're going to be doing something called radioactive dating, which is when we basically take a look at certain radioactive elements and look at how long they take to decay. And the reason why this is helpful to us is because they decay at set and predictable rates. It tells us, as we know exactly how long it takes for them to decay a certain amount. And the amount that we're going to be paying attention to is 1/2. Okay? Isotopes, all that means is that it's the same element with the same number of protons, but it's going to have a different number of neutrons. And if you guys remember correctly, in an atom, you have protons and neutrons in the middle, and then you have your electrons on the outside. Okay, so radioactive decay, this is pretty important. You have your unstable radioactive parent. So this is the starting one. And it is decaying into a stable daughter. So this is what you are ending with. This is what you are making. All right, daughter versus son. There is no gender assigned here. It is just saying that you have the parent and this is what it's making. So the next generation, okay? So here it's saying you have carbon-14, which is the radioactive parent, unstable, and that is decaying into nitrogen-14, which is the daughter, and this one is stable, okay? So you have this on your Earth Science Reference Tables, page 1, okay? And it's telling you that this is the parent, and it's telling you that it is turning into its daughter. So look, these are their symbols, the parents, and they are turning into these guys, which are the daughters. Okay, so here carbon is turning into nitrogen-14. Potassium-40 is turning into argon and calcium-40. Uranium is turning into lead. Rubidium is turning into cerium. And those numbers are just representing what type of isotope they are. If you don't remember what the symbols stand for, remember you could look on the back page of your reference tables, and that will tell you what the symbols are. And then these numbers over here, these represent the time it takes for 1/2 to decay. All right, so the time it takes for 1/2 of the parent to decay. All right, and these are set numbers. So if we were to break this down, all right, this is in scientific notation. If I were to write it out, this would be 5,700 years, right? I take my decimal and I move it 1, 2, 3 places to the right. If I were to take this, I take my decimal and I have to move it all the way to the right 9 spots. So this would be that many years. All right, so if we were to break that down, that's 1.3 billion years. Same thing with this one. That would be 4.5 billion years. And this one, you should see, it's 10. Oh, that is 49 billion years. Okay? And look, it shows you, based on their half-lives, it shows you what they can be used to date. All right, carbon-14 is very useful in dating organic remains because it's a relatively short half-life. Okay, anything that's super old is not going to be very useful if you're using carbon-14 because the half-lives will just end up really close to zero really fast. Potassium-40 is good for dating granites. Uranium-238 is very good for dating rocks that are very old and around the age of the Earth, right? Okay, so an element's half-life decay rate is not affected by temperature, pressure, or environment. None of those things affect half-life. The only thing that can affect half-life is time, okay? That is the only thing that can affect half-life. Okay, so the time it takes for 1/2 of the parent to decay. All right, and we are going to have to get used to these percentages, but I figure we will do that over here. Okay, so here's your note sheet. I already went through all the notes. I would like to pay attention right here a second. Okay, so this is the amount of parent rock. All right, this is what you are starting with, and then this is the amount of daughter, what you're ending with. And make sure that you pay attention to this number of half-lives. All right, so let's go through it. At 0 half-lives, this means that no time has gone by at all. You will have 100% of the parent, right? Because that is what you are starting with. All right, and this is what you are ending with. So if you have 100% of the parent, you have 0% of the daughter, right? None of the parent rock has decayed yet. Okay, so fine. Now, 1 half-life goes by. One chunk of that half-life has gone by. And in that time, remember what we said, 1/2 will decay. So 1/2 of this parent has decayed. So now we have 50%. Now, that other 50% goes over here. So now at this point, this was 0 half-lives. Now you have 1 half-life. Now you have 50% parent and 50% daughter. Okay? Now, another half-life goes by. So now we're up to 2 half-lives. So the parent gets cut in half again. So 50 cut in half is 25. And then that other 25 is going to be added to the daughter. So 50 plus 25 gives you 75. So this is what you get after 2 half-lives. Okay, so all you're going to be doing every half-life that goes by is you're going to be cutting the parent in half and you're going to be adding it to the daughter. All right, so the next half-life, now we're up to 3 half-lives. You're going to be taking half of the parent. So 25 cut in half is 12.5. And you're going to be adding that other 12.5 to the daughter. So you're going to end up with 87.5. If another half-life goes by, same deal. Cut the parent in half again. And you add that other half to the daughter. Now, usually they wouldn't go past 4 half-lives. If they did, you just keep doing what we're doing. You cut the parent in half and you add it to the daughter, okay? And you could just keep doing that. Now, my question to you is, will you ever hit 0? If you just keep cutting numbers in half, do you ever hit 0? That answer should be no. You get really close to 0, but it will never hit 0, okay? All right, so here's your worksheet that I want you guys to do. Again, it goes hand in hand with the notes. You guys should be able to handle 1 through 6. I want you guys to get 1 through 7 done. Okay, 1 through 7 is what I want you to get done today. We'll get to the rest of the worksheet next time. All right, going back to this, this is just showing you what it would look like. So we're just taking those numbers that we just used and plotting them. And if you look, the radioactive isotope, which is the parent, decays over time. Notice the line has gone down. And the daughter will go up over time because that one's getting bigger over time. Okay? So daughter goes up and the parent goes down. All right, so common regions question. So here the diagram represents a sample of rubidium. So this is the parent. Which diagram represents the correct proportion of rubidium to its decay product, cerium? So this is the daughter. After 2 half-lives. All right, so 2 half-lives go by. So that means you're going to be cutting it in half twice. So 1 half-life, right? So half of rubidium would be left. And then if another half-life were to go by, it would get cut in half again. So your answer should be choice 2. All right, so here's another one. Let's check it out. Here, the table below shows information about the radioactive decay of carbon-14. Carbon-14, that is the parent. All right, remember, you could always look at your reference tables, page 1, okay? This is saying mass of the original, so this is parent. And this is saying how many years have gone by. Okay, because if you remember, if you look it up, this is how many years 1 half-life is for carbon. And you can see that here, right? 1 half-life is 5,700 years. 2 half-lives, it's 5,700 times 2. 3 half-lives is 5,700 times 3. And then you just keep adding 5,700 years for every half-life that goes by. So if it's asking you how much of carbon-14 would you have after 28,500 years, well, let's do a little math here. If you have 17,100 and then you were to add another 5,700 years, that would be 4 half-lives. Oh, I just gave you the answer. 4 half-lives. And that would be 1 over 16, and that would be 22,800 if I were to add another 57. If I were to add another 5,700 years, that brings us to our magic number that they're asking for. That would be 5 half-lives, and I would just cut it in half again. And that is why your answer was choice 3. All right, because every half-life that goes by, the parent gets cut in half. Okay? That chart that we just went over, the parent getting cut in half every single time and the daughter growing by a half every single time, that is something that you should be able to memorize. If not memorize, just work your way through. All right, so that's about it. Please make sure that you get the worksheet done and your lab and Castle Learning done. And I will talk to you tomorrow. Hope everyone has a good day.